5th of September 1977, 8:56 in the morning Eastern Daylight Time. From Launch Complex 41 at Cape Canaveral, Florida, a Titan 3E Centaur rocket lifted off with a small spacecraft riding on top. Just over 700 kilograms of it, the size of a small car. They called it Voyager 1. It was built to fly past Jupiter and Saturn, photograph their moons, send back its data, and, by the plans of the engineers of the time, fall silent somewhere beyond the planets in about 20 years. Almost 50 years later, Voyager 1 is still speaking. Its radio signal takes 23 hours to reach the Earth. In November of 2026, about 3 months after you are hearing this, it will become the first thing built by human hands to be separated from us by a full light day. 24 hours, one way. A short exchange of, "How are you doing?" and "I am fine," would take 48 hours end to end. It is roughly 25.5 billion kilometers from the Sun, about 170 astronomical units. One astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometers. So, Voyager 1 right now is 170 times farther from the Sun than we are. And here is the strange part. In spite of 50 years of flight at 61,000 kilometers per hour, roughly 70 times faster than a passenger jet at cruising altitude, Voyager 1 has not yet covered even 1% of what we today consider our solar system. 1%. Less than that. Because out there, in the direction it is flying, sits a huge structure we only came to understand in the last century. It wraps our Sun in a sphere stretched almost halfway to the nearest star. Voyager 1 will only enter it a few hundred years after we are all gone, and come out the other side of it only after some 30,000 years. It is called the Oort Cloud. Tonight, we are going to travel there. Slowly. Part by part. Because to understand the Oort is to understand where our home really ends. Before we go any further, let me tell you about 3 events, 3 dates, 3 names. They will come back through the rest of this film many times. Hold on to them, they are the thread we will follow. 5th of September, 1977, Cape Canaveral. Voyager 1 lifts off. That is where we begin. 1st of April, 1997. Comet Hale-Bopp reaches its closest point to the Sun. For 18 months, night after night, people around the world can see it with the naked eye. It came in from the Oort Cloud, for the first time in about 2,500 years, and, when this pass is finished, it will drift back out again for thousands of years more. 21st of September, 2024, New York City. The Hayden Planetarium in the American Museum of Natural History. An astronomer named Jackie Faraday is watching a simulation from David Nesvorny's spin on the Great Dome, a simulation run for 5 months on the Pleiades supercomputer at NASA. And she sees, for the first time, the shape of the Oort Cloud. It turns out to be a spiral. 3 dates. Almost 50 years ago. Almost 30 years ago. 2 years ago. 3 bridges across a single cloud. Now let us turn our mental camera on the solar system and look at it honestly. Take the diagram from your school textbook. The Sun at the center, Mercury, Venus, Earth, Mars. Then a thin band of asteroids between Mars and Jupiter, Jupiter, Saturn, Uranus, Neptune. Usually Pluto sits next to them too, even though it was renamed a dwarf planet in 2006. And then the diagram ends. Empty white paper. Nothing more. That is what the textbooks show, what school taught us, what still hangs on the pencil case posters at museum gift shops. 8 planets, or 9 if you gently disagree with the 2006 decision, and nothing around them. The problem is that this picture is a lie of omission. Not because the planets are drawn wrong, they are drawn correctly, but because the diagram stops almost exactly where the real solar system begins. Take Neptune. It is the farthest of the big planets we know, about 30 astronomical units from the Sun. A year on Neptune lasts 165 Earth years. Sunlight is 900 times weaker out there than it is here. Noon on Neptune looks like a late winter dusk in Moscow. Now take Voyager 1. It is at 170 astronomical units, almost 6 times farther from the Sun than Neptune. If the school diagram were right, Voyager 1 should have been out in interstellar space long ago. It should have left the solar system, but it has not. It is still at the very beginning of the solar system. To understand why, we need 3 boundaries. 3 different answers to the same question. Where does the Sun end? People confuse them all the time, and half of the misunderstanding about the Oort Cloud comes from that confusion. Boundary 1. The heliopause. This is a plasma boundary. The Sun is constantly throwing out a stream of charged particles, protons, electrons, alpha particles. That stream flies outward at about 400 kilometers per second, and it fills a huge magnetic bubble around the Sun called the heliosphere. That bubble ends where the solar wind is finally balanced by the pressure of the interstellar gas outside it. That balancing point is the heliopause. It sits at roughly 120 astronomical units from the Sun. Voyager 1 crossed the heliopause on the 25th of August, 2012. Scientists knew because the density of solar wind particles fell sharply, and the background cosmic radiation rose at the same moment. Voyager 2 crossed it on the 5th of November, 2018, at about 119 astronomical units. The headlines around the world in 2012 said, "Voyager has left the solar system." The headlines were wrong. Voyager 1 left the heliosphere, that small magnetic bubble the Sun blows around itself. It did not leave the actual solar system. Beyond the heliopause, Voyager is still deep inside the Sun's gravitational domain, and its motion is still shaped by the Sun far more than by any other star. But it is not gravitationally bound to the Sun any longer. Its trajectory is hyperbolic. Its speed is above the escape velocity for its distance, and it will not return. The heliopause is a boundary between magnetic realms, not a gravitational one. Past it, the Sun is still the master of everything that turns around it. Boundary 2. The orbit of the farthest known body. Right now, the farthest known object in the solar system, with a well-established orbit, is far, far out, catalogued as 2018 AG37. It was about 132 astronomical units from the Sun when we found it. Its estimated aphelion, the farthest point of its orbit, is a few hundred to over 1,000 astronomical units. If we take the best measured extreme orbit instead, that is Sedna. Sedna's aphelion is 937 astronomical units. By that boundary, the outer edge of the most distant orbit we have confirmed, the solar system ends somewhere around 1,000 astronomical units from the Sun, 8 times farther than the heliopause, still terrifyingly close to the true edge. The problem with this definition is that it keeps moving. Every few years we find a more distant object. 15 years ago, the farthest known thing was Pluto. Then came Sedna. Then far, far out. 10 years from now, the record will be somewhere further still. This is the edge of what we have seen, not the edge of the system. The real edge is Boundary 3. Boundary 3, the Hill sphere. This is the gravitational edge of the solar system. It is the radius at which the Sun's pull is still stronger than the combined pull of the nearest stars. Inside that sphere, a body belongs to the Sun. Outside it, the Sun has to share, and eventually loses, to the galactic pull. The Hill sphere of the Sun is estimated at somewhere between 100,000 and 200,000 astronomical units. The range is wide because it depends on exactly where the nearest stars are today and how their gravity is pulling on us. An average value is about 1 parsec, roughly 3¼ light years. Just under the 4¼ light year distance to Proxima Centauri, the closest star to us. Between the heliopause at 120 units and the Hill sphere at 100 to 200,000 units, The gap is a factor of 1,000 or more. Between Sedna's orbit at 900 units and the Hill sphere, the gap is a factor of 100. Our usual sense of the size of the solar system is off by 1,000-fold. So when we say that Voyager 1 has covered less than 1% of the system, that is not rhetoric and not exaggeration. It is arithmetic. It is at 170 astronomical units, and the outer gravitational edge is at least 100,000. Divide the first by the second. Less than 2/1,000ths of the way. Over the next 300 to 500 years, depending on where exactly the inner edge of the cloud sits, and current NASA estimates favor the near end of that range, it will reach the inner edge of the Oort Cloud. Over the next 30,000 years or so, it will pass through and come out the other side. But its plutonium batteries, which power its radio transmitter today, will fall below the threshold to speak by around 2036. Which means the entire crossing of the Oort will happen in silence. We will never know what Voyager saw out there. Let me pause here and put a few things in perspective because Voyager 1 is the most successful robot ever built by human hands. 5th of March, 1979. Voyager 1 passes Jupiter, 349,000 kilometers above its cloud tops. 52 hours of close encounter. During those 2 days, it discovers a thin dust ring nobody knew about. It discovers active volcanoes on the moon Io, the first time humans ever see a live geological process outside the Earth. It photographs the Great Red Spot in detail. It measures Jupiter's magnetic field, which turns out to be tens of times more powerful than the Earth's. 12th of November, 1980. It arrives at Saturn. It finds several small moons nobody had catalogued. It discovers a dense atmosphere around Titan, an orange, nitrogen and methane fog blanket. It resolves the detailed structure of Saturn's rings. Because Titan matters so much scientifically, Mission Control decides to send Voyager 1 on a trajectory that gives Titan a good look, even at the cost of any future flyby of Uranus and Neptune. From that day, and for the next 45 years, Voyager 1 has been climbing at about 35 degrees above the plane of the planets, heading toward the northern galactic pole. On the 14th of February, 1990, 6 billion kilometers from the Sun, Voyager 1 turned its camera around one last time, at the request of Carl Sagan, and took its final picture of home. A tiny blue speck, 1/10 of a pixel wide, sitting in a shaft of scattered sunlight. Sagan wrote a book about that image in 1994. He called it Pale Blue Dot. It is still one of the most famous photographs ever made. After that picture, Voyager 1's cameras were shut down. There was no longer anything ahead of it bright enough to be worth photographing. From then on, it has sent home only data from its other instruments: the magnetometer, the plasma detector, the cosmic ray counter. Those instruments are the ones that told scientists, in 2012, that it had crossed the heliopause. And Voyager 1 is not the only thing we have sent in that direction. Voyager 2, its twin, launched 16 days earlier, on the 20th of August, 1977, along a different path. It is at about 142 astronomical units, moving a little slower, heading in the general direction of Sirius. It will pass close to Sirius in about 296,000 years. Pioneer 10 and Pioneer 11, the older siblings. Launched in 1972 and 1973. Both have been silent for years. Pioneer 10 since 2003, Pioneer 11 since 1995. But they are still flying. Pioneer 10 is heading generally toward Aldebaran, which it will reach in about 2 million years. And New Horizons. Launched in 2006, it made its close pass by Pluto in 2015, then met the small object Arakoth in 2019. It is at about 60 astronomical units now, moving at 3 units a year, still awake, still working. In a few decades it too will fall quiet, in the general direction of Sagittarius. 5 spacecraft. 5 small metal points, drifting through millions of billions of kilometers of vacuum. None of them will reach the edge of the solar system, no matter how long they work. Our fastest machine, over half a century, has crossed 1% of what we now call our cosmic address. This should sink in as a fact, not as a scare. The Oort Cloud has not yet been observed directly at its typical outer distances. It is still a hypothesis, though a very strongly motivated one. And the comets that fall through the inner solar system give it away every few years. Hale-Bopp in 97, Hyakutake in 96, Neowise in 2020, Tsuchinshan Atlas in the autumn of 2024. Each of them was born in the Oort, billions of years ago, fell inward under some slow trigger, ran through the planetary zone in a matter of years, swung around the sun, and then began the long climb back out. So the Oort exists, is populated, and holds roughly 1 trillion pieces of ice. We simply have not yet learned to see them directly, on their own, out where they live. How did we work all this out, if we have never seen the Oort itself? Who was the first to think of it? Where were they right, and where were they wrong? That is the next part. To understand where Voyager is going, we first have to understand where what we already know actually ends. And that means at least 40 years of history, and one name that would be unfair to skip. Jan Oort saw the pattern in 1950, in the orbits of 19 comets. But he was not the first. 18th of February, 1930. Flagstaff, Arizona, Lowell Observatory. A young assistant named Clyde William Tombaugh places 2 photographic plates under the blink comparator. On both plates, the same field of stars, in the constellation Gemini, taken 6 nights apart. He looks through the eyepiece and flicks between the 2 plates with a small mechanical switch. And he sees one tiny point among the thousands of stars shift slightly. That is how Pluto was discovered. Tombaugh was 24. He had not finished university. Lowell had hired him because of hand drawings of Mars and Jupiter he had made on his family's Kansas farm, using a telescope he had built himself. The drawings were so precise that the observatory's director wrote back inviting him out to Flagstaff. Pluto at that moment was about 40 astronomical units from the Sun, farther than Neptune. It was the most distant thing humans had ever seen as a distinct object. They named it after the Roman god of the underworld, because where Pluto lives, everything is dark and cold. The name was suggested by an 11-year-old girl from Oxford, Venetia Burney. Her grandfather had read out the newspaper story at breakfast, and she said, over her cereal, "Pluto." The grandfather wrote to the observatory. The observatory agreed. For 76 years, Pluto was the 9th planet of the solar system. Then, on the 24th of August, 2006, the International Astronomical Union met in Prague and voted differently. Pluto was reclassified as a dwarf planet. No school textbook printed since is entirely certain how many planets we have, 8 or 9. People took it personally, not because of the formality, but because they felt Pluto had been erased. That reaction is not naive. It is a reaction to being shown, again, an incomplete picture. The Prague decision did not remove Pluto from the solar system. It recognized that Pluto is not a lone straggler at the far edge, but the first known member of a large family we had barely begun to see. Because beyond Neptune, out past Pluto's orbit, there is not empty space. There is the Kuiper Belt. The idea of that belt had been circulating for decades. The Irish astronomer Kenneth Edgeworth suggested it in 1943. The Dutch-American astronomer Gerard Kuiper suggested it in 1951. Both of them argued that beyond Neptune, there should be a broad region of small, icy bodies, left over from the formation of the solar system. For 41 years, the idea remained a hypothesis. Nobody could confirm it. The bodies were too dim, too far away to see. On the 30th of August, 1992, 2 astronomers working on the University of Hawaii's telescope on Mauna Kea, David Jewett and Jane Liu, detected a small point of light that moved. It was catalogued as 1992 QB1, an icy body around 160 kilometers across, orbiting between 40 and 45 astronomical units from the Sun, the first confirmed member of the Kuiper Belt, other than Pluto itself. Since then, we have found more than 3,000 of them. Estimates suggest there are at least 100,000 Kuiper Belt objects larger than 60 kilometers across, and perhaps 1 billion larger than a mile. Among the largest we know are a family of dwarf planets. Eris. Imaged on plates taken in 2003 by Mike Brown, Chad Trujillo, and David Rabinowitz, identified as a moving object in January 2005 and announced to the world in July of that year. It is about 2,326 kilometers across, almost the size of Pluto. It was Eris that finally forced the International Astronomical Union to redefine the word planet. Because if Pluto is a planet, then so is Eris, and so are several dozen more. Haumea. Discovered in 2004, a strange body, stretched into an American football shape, spinning on itself every 4 hours, orbited by 2 small moons and even by a thin ring. It is the only known dwarf planet with a ring, named after a Hawaiian goddess of fertility. Makemake. Discovered in 2005, about 1,400 kilometers across, named after the creator god of the Rapa Nui people of Easter Island. Quaoar. Discovered in 2002, about 1,100 kilometers across, also with a ring. Gonggong. Discovered in 2007, about 1,200 kilometers across, named after a Chinese water god who, in the creation myth, breaks the pillar that holds up the sky. Orcus. Discovered in 2004, about 900 kilometers across. Its orbit is a mirror image of Pluto's. Where Pluto is, Orcus is not, and the other way around. Sedna. Discovered in 2003. We will come back to Sedna in her own right, because she is no longer really Kuiper. All of these are relatives. All of them were formed from the same leftover disk of small material that stayed behind after the big planets found their orbits. All of them are cold, minus 220 degrees Celsius and below. All of them are rich in water ice, methane ice, ammonia ice. The Kuiper Belt is not a thin, empty scattering of dust. It is a dense, populated zone. There is one important thing about it that we have to notice. It is flat. All the Kuiper Belt objects turn around the Sun more or less in the same plane as the planets. Individual orbits can tilt. Pluto's is inclined by 17 degrees, for instance, but the belt as a whole is a disk. The same disk as the planetary system, a little wider. And it ends at about 50 astronomical units, at what is known as the Kuiper Cliff, a place where the density of objects drops sharply. Beyond the cliff is the scattered disk, a less crowded region made of more chaotic orbits, reaching out to hundreds of astronomical units. Objects like Eris live there, on very elongated, tilted paths. They are probably there because Neptune, in the first few 100 million years of the solar system, threw them out on those wide orbits when the planets were still moving into place. There is one more thing we should say about Pluto itself, because since 2015, we have a portrait of it that no century before ours has had. On the 14th of July, 2015, the New Horizons probe passed 12,500 kilometers above the surface of Pluto, at almost 50,000 kilometers per hour. In the few hours around closest approach, it sent home more data than every ground observation of Pluto for the previous 85 years combined. Pluto turned out to be far more active than anyone had expected. It has smooth ice plains only a few tens of millions of years old, impossible without some source of internal heat. It has mountains 3.5 kilometers tall, built out of water ice, because at Pluto's temperature, ordinary rock could not have supported that weight, but water ice behaves like stone. It has nitrogen glaciers, slowly flowing down from the highlands into the lowlands. It has a thin nitrogen atmosphere that puffs up as Pluto swings closer to the Sun and contracts back as it moves away. Pluto has 5 moons. The largest is Charon, half the diameter of Pluto itself, which makes them effectively a double body. The point they turn around lies out in space between them, not inside Pluto. The smaller moons, Nix, Hydra, Kerberos, Styx, each have their own quirks. New Horizons kept going. On the 1st of January 2019, it flew past a much smaller Kuiper object, officially named Arrokoth, about 36 kilometers long. Arrokoth turned out to be an unusual thing. Two round lobes stuck together, like a snowman built from two balls of icy dust that had joined at the moment of the solar system's formation. The first close portrait of a small, typical Kuiper body. Now, here is where the first suspicion enters. We see plenty of icy bodies in the Kuiper Belt and the scattered disk. We see plenty of short-period comets, the ones that come back to the sun every couple of centuries or less. That period, less than 200 years, tells us they came from a region that is not so far away. And they do. Short-period comets come from the Kuiper Belt and scattered disk. Their orbits, like the bodies out there, lie more or less in the plane of the planets. But there are other comets. Long-period comets. Periods of thousands of years, tens of thousands, hundreds of thousands. Some of them come back only once every few million years, or perhaps only once ever. And here is where things get interesting. Their orbits do not come to us from the plane of the planets. They come at us from every direction. Hyakutake in 1996, Hale-Bopp in 97, Donati in 1858, still remembered because Donati worked in the age just before photography, and artists sketched the comet for the newspapers. Ikia Seki in 1965, West in 1976, Neowise in 2020, Tsuchinshan Atlas in the autumn of 2024. If you plot the incoming directions of long-period comets on a globe of the sky, they are spread evenly across it. Some fall in from the direction of Orion, some from the Southern Cross, some from the northern galactic pole, some from the south. That can mean only one thing. The reservoir of long-period comets is not a disk, it is a sphere. Something that wraps the solar system from every side, not only from the plane. Something huge enough that a comet falling out of it can enter our field of view from any direction at all. The first person who worked this out clearly was not Jan Oort. He was the first to prove it. But the idea itself was already in the air. The Kuiper Belt explained the short-period comets. The Kuiper Belt did not explain the long ones. So beyond the Kuiper Belt, there had to be something else. Not in the plane, genuinely far. And beyond the reach of any telescope of the time. The solar system's textbook diagram, the one that stops at Neptune, is not wrong for showing 8 planets. It is wrong for showing nothing beyond them. Neither Neptune nor Pluto is the edge. Neither the Kuiper Belt, nor the scattered disk, nor even the heliopause that Voyager crossed in 2012. All of these are only the last rooms in the front of the house. If we compare the solar system to a house, with the sun as a fireplace in the living room and the Earth as a chair in front of it, then Pluto is somewhere near the door. The Kuiper Belt is the porch. The heliopause is the fence in front of the porch. Beyond that fence is the property. Enormous, dark, thousands of times larger than the house itself, still belonging to the family that owns the house. And to look at that land honestly, we have to look at it separately, because it is older and larger than the house. That land is the Oort Cloud. It stretches from about 2,000 astronomical units at the inner edge, out to 100,000 or 200,000 at the outer edge, depending on how we measure. That is from about 70 times the distance of Neptune, out to about 6,500 times the distance of Neptune. It surrounds the sun not as a belt, not as a disk, but as a sphere. Nearly all of the bodies inside it are frozen chunks a few kilometers to 140 kilometers across. Light from the sun takes 11 days to reach the inner Oort, and nearly 2 years to reach the outer edge. Solar gravity out there is a few billion times weaker than what we feel at the Earth. A single orbit around the sun, at those distances takes millions of years. And in this vast sphere, at any moment, there are at least hundreds of billions of icy bodies. By less conservative estimates, over 1 trillion of them. How did we work all this out without ever seeing one of these bodies in place? Through comets, through mathematics, and through a single 14-page paper published in 1950 in the Bulletin of the Astronomical Institutes of the Netherlands, Volume 11, number 408. It listed 19 numbers, the orbital periods of 19 long-period comets. And it drew a conclusion that changed what the phrase solar system was allowed to mean. His name was Jan Hendrik Oort. He was not the first to suspect that a distant reservoir of comets had to exist beyond Neptune. 18 years earlier, in 1932, the Estonian astronomer Ernst Julius Öpik, then working at Harvard, published a mathematical argument for the same thing. Öpik's paper did not travel widely, but it was first. Oort came to the same conclusion independently, 18 years later, and unlike Öpik, he had the instrument to prove it, 19 carefully measured orbits of long-period comets. Who this man was, what he calculated, why his name became attached to a cloud whose idea Öpik had already framed, and why, 75 years after Oort's paper, we still have not seen a single Oort Cloud object directly. That is the next part. 1932. Liverpool, and then Harvard. The Estonian astronomer Ernst Julius Öpik is working on a problem that most of his generation is not interested in. He is asking what happens to a comet's orbit when it comes back to the Sun 1,000 times. Each pass through the planetary region changes its path a little. Jupiter, the most massive planet, tugs on it more than all the others. Over 1 million years, over 10 million, over 1 billion, those small tugs add up. Comets should either be pulled onto shorter orbits or thrown out of the solar system entirely. Öpik sits down and calculates, and he sees that something has to be different from the simple picture. If the only comets around the Sun were the ones we can see today, they would already be gone. Over a few 100 million years, every long-period comet we ever observe would have crashed into a planet, or been captured onto a short-period orbit, or escaped into interstellar space. And yet, the long-period comets keep coming. Which means there is a permanent reservoir out there, somewhere very far, because if it were close, the same processes that clear out the short-period comets would have cleared it long ago. And if it were closer than a few tens of thousands of astronomical units, passing nearby stars would have unbound it over the age of the solar system. Öpik publishes his paper. It appears in the Proceedings of the American Academy of Arts and Sciences, Volume 67, in 1932. The work does not circulate widely among astronomers of that era. The idea slips into the shadows. Öpik died in 1985, at the age of 91, and lived long enough to see the same idea become world-famous under another man's name. He never complained. He was one of those scientists who believed it did not matter whose name was on a hypothesis. What mattered was that the hypothesis was right. 1950. Leiden, in the Netherlands. Jan Hendrik Oort, director of Leiden Observatory, one of the most respected astronomers in the world. He is 49. He already has, behind him, the discovery that our galaxy rotates. He showed this in the 1920s by measuring the speeds of stars near the edge of the Milky Way, and the discovery that the Sun sits not at the center of the galaxy, but about 2/3 of the way out from the middle. He takes the data on all known long-period comets. There are not many of them, fewer than 100. Out of those, he selects the ones with almost parabolic orbits, that is, orbits so stretched out that a full return to the Sun would take hundreds of thousands, sometimes millions of years. 19 of them meet his criteria. He builds a histogram. On the horizontal axis, the distance of the aphelion, the farthest point of each comet's orbit. On the vertical axis, how many comets fall into each bin. And he sees the pattern. Almost all 19 cluster in a single range, 20,000 to 50,000 astronomical units. That is not a coincidence. If long-period comets were arriving at random from a variety of far-off places, the aphelion distances would be spread out evenly. This is a tight cluster, which means the Sun has a reservoir that dumps comets inward, and that reservoir sits at 20,000 to 50,000 astronomical units. And because those comets can arrive at the Sun from all directions of the sky, not just from the planetary plane, that reservoir is not a disk. It is a sphere. Oort publishes his paper in June 1950, 14 pages. Bulletin of the Astronomical Institutes of the Netherlands, Volume 11, number 408. The title is deliberately long and precise. The structure of the cloud of comets surrounding the solar system and a hypothesis concerning its origin. From that paper onward, the cloud has been called the Oort Cloud. Not because Oort was the first to think of it. Öpik was there 18 years earlier. Because Oort was the first to build a quantitative observational case for it. Oort's hypothesis sounds like this. The Sun has a distant, spherical reservoir of loosely bound icy bodies. They orbit slowly out there, millions of years for a single revolution. Occasionally, a neighboring star drifts past the solar system. Its gravity nudges the cloud. Individual bodies pick up small kicks. Some of those kicks add speed and send the body flying out into interstellar space. Others subtract speed, which drops the body's orbit inward. And then, over thousands of years, that body slowly falls toward the Sun. It swings through the planetary region, warms up, releases gas, grows a tail, and we see it as a long-period comet. Some pass through and swing back out for another tens of thousands of years. Some are caught by Jupiter's gravity, slowed down, and demoted to the short-period family. Some fall into the Sun outright, or fragment, and disappear. Oort's model had few precise numbers. He could not say how many bodies were in his cloud. He could not say exactly where its inner and outer edges lay. He could not prove that it existed at all, only that it had to. But he could answer the biggest question of his time. Why are there long-period comets when Jupiter should have scattered them all away over the age of the solar system? Because, said Oort, they keep falling in from a huge reservoir that keeps refilling the supply. 75 years later, we know Oort was right. Details have been refined. The inner Hills cloud, which Oort had no way to predict, was proposed only in 1981. The mechanisms turned out to be more complicated, not just passing stars, but also galactic tides and giant molecular clouds. Estimates of the number of bodies have grown from billions to trillions. Estimates of the total mass have moved from a vague, quite a lot, to about 40 Earth masses. But the frame of the model, drawn on 14 pages in 1950, still holds. There is a separate thing to credit Oort with. He showed that we can learn about what we cannot see, through what we can. That is a rare move in science. It was how dark matter was first suspected. It was how, later, the first planets around other stars were discovered, by the way those stars wobble. It is how much of modern astronomy works, in every case where the object we are studying is too dim to photograph directly. Now here is a simple question. Why, in 75 years, have we still not photographed a single Oort cloud object on its own? The answer is arithmetic. Take a typical body in the inner Oort, 20 kilometers across. That is about the average size of comet nuclei that we have measured. 20 kilometers, for perspective, is slightly more than the diameter of central London, or about the width of St. Petersburg along its ring road. Now move that object out to 100,000 astronomical units from us. That is about 1.5 light years. How bright would it look on our sky? The answer, worked through the formula for apparent magnitude, is about 42. What does 42 mean? The brightest star in our sky, Sirius, has an apparent magnitude of -1.46. The full moon is -12.7. The sun is -26.7. The dimmest star a human eye can see, from a very dark sight on a perfect night is about 6.5. The largest ground-based telescopes in use today can register objects down to about magnitude 28 or 29, with very long exposures. The Hubble Space Telescope, after many hours of accumulation, reaches about 31. The James Webb Space Telescope, about 31 to 32. The gap between magnitude 31 and magnitude 42 is 11 powers of 10 in brightness, roughly 600,000 times dimmer than what our best space telescope can detect at all. We physically do not see Oort cloud bodies because they are too faint. Even if we knew exactly where to point our lens, the photons from a 20-kilometer ice ball at 100,000 astronomical units simply do not arrive at our sensors in numbers that can be told apart from noise. There is exactly one case where we do see them. It is when one of them falls inward and turns into a comet. Once such a body comes within about 10 astronomical units of the Sun, the ice on its surface starts to sublime, go straight from solid to gas, skipping the liquid stage. A coma forms around the nucleus, a fuzzy shell of gas and dust. And the coma is thousands of times brighter than the nucleus itself because it scatters sunlight in every direction. The comet becomes visible. We can measure its orbit, its chemistry, its trajectory backward through space. But that is a rare event. From about 1690, when Edmund Halley first calculated the orbit of a comet and gave it his name, up to today, we have seen and studied a few hundred long-period comets in reasonable detail. Out of an estimated trillion bodies, that is roughly 1 in a few billion. A lawn in your backyard with 1 trillion blades of grass on it, and once a year, one of those blades sends you a postcard. From those postcards, you have to figure out the size of the lawn, how many blades it has, where it is, and what the grass is made of. Astronomers figured it out. But the model they built is a statistical one. It is not about specific objects out there. It is about how many should exist, how they must be distributed on average, what forces must be nudging them around. It took another 3 decades after Oort's paper before the model started to be refined in an important way. In 1981, a physicist in New Mexico looked at Oort's numbers and noticed a problem. Oort's cloud, by his calculation, should have been almost fully drained by now, worn away by passing stars over 4.5 billion years. And yet, comets kept falling in, which meant something else had to be there, closer, denser, still supplying the sky. That physicist was Jack Hill's. His inner cloud, how he found it, what shape he gave it, and the first object we finally caught inside it in 2003 is the next part. The 1980s. Los Alamos, New Mexico, the national laboratory known for the wartime atomic bomb project. In peacetime, Los Alamos is a large research center, and among the physicists there are the astronomers who work on gravitational dynamics. One of them is Jack Hill's. His specialty is stellar dynamics, the mathematics of how large, loosely bound systems of many bodies behave under rare but strong outside forces. In practical terms, he is asking how the Oort cloud evolves over billions of years when other stars pass by from time to time. Hills sits down with the numbers, and he sees the problem immediately. If the Oort cloud is exactly what Oort described, a sphere of loosely bound bodies from 20,000 to 50,000 astronomical units, then over the 4.5 billion years since the solar system formed, passing stars should have almost completely emptied it. Each nearby stellar pass gives the cloud a small gravitational tug. Over 1 billion years, the tugs add up enough to unbind a fraction of the outer bodies. Over another billion, another fraction. By 4.5 billion years, only 1/10 of the original cloud should remain, perhaps only 1/100th. And yet, comets are still falling in. Which means the reservoir has not been drained. Which means something must be refilling it. Hills reaches the conclusion that there has to be a second cloud. Not the outer, spherical one Oort described. Something else. Closer to the sun, denser, and stable, because passing stars at their typical distance of a few parsecs cannot reach it with their gravity. In 1981, he publishes his paper in the Astronomical Journal. The title is Comet Showers and the Steady-State Infall of Comets from the Oort Cloud. In the paper, he lays out an inner cloud, roughly 2,000 to 20,000 astronomical units from the Sun. Not a sphere, but a flattened torus, because it is populated by bodies that were originally scattered outward by the young Jupiter and Neptune along orbits that lay in the plane of the planets. After several billion years, passing stars have not yet had time to fully mix that torus into a sphere. And this inner cloud should have 5 to 100 times more bodies than the outer one. From now on, that region is called the Hills Cloud. As the outer Oort Cloud slowly loses its residents, worn away by passing stars, the Hills Cloud slowly replaces them. Objects diffuse outward from the inside, and from time to time, when a star passes close enough, whole waves can be knocked loose from the Hills Cloud and sent falling inward. Comet showers. Periods in the Earth's history when, over tens of thousands of years, unusually large numbers of comets fall toward the Sun. Hills's model solved 2 problems in one move. Why comets are still arriving 4.5 billion years later? Because there is an inner reserve. And why the geological record of the Earth has occasional short intervals of extra bombardment, because when a close passing star hits the Hills Cloud, a shower spills inward. But Hills's model, like Oort's, was thin on numbers. He could not pin down the exact inner edge. He could not prove the cloud existed. He could only show that it had to. 22 years passed between his paper and the first observational hit. 14th of November, 2003, Palomar Observatory. Mike Brown, Chad Trujillo, and David Rabinowitz are searching for large, very distant bodies. They have already found a few big scattered disk objects by this point. Tonight they are looking in a patch of sky where nobody has looked before, for objects that move extremely slowly, because slow motion means very distant orbits. One point of light is moving. Slowly, the shift is only visible between images taken several hours apart. They take another set of images a few nights later. The point has moved again, and again a few nights after that. They calculate the orbit, and they get something nobody has ever seen. Perihelion, 76 astronomical units. Aphelion, 937. Period, 11,400 years. For comparison, Pluto's perihelion is 29 astronomical units. Pluto's aphelion is 49. Pluto's period is 248 years, which means the new object, at its closest approach to the Sun, is already 2.5 times farther than Pluto ever gets at its farthest. At its own farthest, it is 20 times more distant than Pluto. No known Kuiper Belt object or scattered disk object flies like that. Kuiper bodies come into about 30 or 40 astronomical units. Scattered disk objects can go out to hundreds, but their perihelia are also nearby, because their orbits were shaped by Neptune throwing them out of the inner regions. To have a perihelion at 76 units, an object would have had to be scattered by something farther out than Neptune, or by some very old event that has not repeated. They call it Sedna. In Inuit myth, Sedna is the goddess of the sea, who lives at the bottom of the Arctic waters where no sunlight ever reaches. Sedna is about 1,000 kilometers across. In color, she is reddish-brown, probably a mixture of frozen methane, frozen nitrogen, and tholins, complex organic molecules formed when simple hydrocarbons are hit by ultraviolet light. Similar tholins coat the surfaces of Pluto and Triton. Sedna's discovery gave astronomers the first possible observational bridge toward the inner Oort population. Near the inner edge of the Oort cloud, there really does seem to live a family of bodies whose perihelia lie far past Neptune. Sedna did not stay alone for long. 2012. An object catalogued as 2012 VP113, discovered by Scott Shepard and Chad Trujillo, the same pair, in part, who found Sedna. Perihelion at 80 astronomical units, aphelion around 450, orbital period over 4,000 years. Because its shorthand designation sounds a bit like the initials of the American vice president at the time, it was jokingly nicknamed Biden. It still lacks an official name because its orbit has not been pinned down precisely enough. 2015. Object 2015 TG387, whose official name is Leleakuhonua. In Hawaiian, that name belongs to a spirit that connects the earth and the sky. About 300 kilometers across. Perihelion 65 astronomical units, aphelion above 2,000, period around 32,000 years. Goes even farther than Sedna, 2018. Object 2018 AG37, informally called Far Far Out. One of the most distant bodies in the solar system that we have ever spotted directly. At its discovery, it was 132 astronomical units from the Sun. 2021. Comet C 2014 UN-271, discovered originally in 2014 by Pedro Bernardinelli and Gary Bernstein in archived dark energy survey images. At the time of publication, it was about 20 astronomical units from the Sun, near the orbit of Uranus. Hubble measurements pinned its nucleus at about 140 kilometers across. That is the largest known Oort Cloud nucleus. The previous record holder, Hale-Bopp, was about 40 to 80 kilometers. Bernardinelli-Bernstein is nearly twice that. It is slowly falling inward. Its perihelion, 10.9 astronomical units, just beyond the orbit of Saturn, will be reached in January 2031. Closer than that, it will not come. It will grow a tail, but it will not become a naked-eye comet from the Earth, too far, too shallow an angle from the Sun. Its importance is not its brightness. Its importance is that it is direct evidence that the Oort holds bodies at least 140 kilometers across, and probably larger. The cloud is not only vast in numbers, it also contains truly large objects. There is more we have found out there in the past 20 years. Several dozen extreme, scattered disk bodies, whose orbits are clustered in a strange way. Their perihelia all point roughly toward the same region of sky, and their orbital planes tilt in roughly the same direction. That coincidence is rare, and it is usually explained by one of three things. A gravitational shepherd, a large, still undiscovered planet orbiting in the outer solar system, or the wake of an ancient stellar passage, or a resonant interaction with the cloud itself. The most famous version of the shepherd idea is Planet 9. It was proposed in January 2016 by Konstantin Batygin and Mike Brown, that same Brown who once found Sedna. They noticed that the orbits of 6 known extreme scattered disk bodies clustered surprisingly tightly. The probability of chance was, by their reckoning, less than 1%. Their conclusion was that somewhere between 400 and 800 astronomical units from the Sun, there ought to orbit a planet of 5 to 10 Earth masses, whose gravity binds the orbits of those 6 objects into a single beam. The planet has not been found. It is being searched for, with telescopes on Mauna Kea, with Subaru, with the Zwicky Transient Facility, and from 2026, with the Vera Rubin Observatory, which we will come to. It may exist. It may turn out to be an artifact of a small sample. 6 objects happen to line up because we have simply not yet discovered enough of that population. The answer will come in the next several years. Now here is the real question. Where did all of this come from? How did the inner Oort and its outer edges end up populated with trillions of icy bodies, including large ones like Bernardinelli-Bernstein and Sedna? Who put them there? The answer is Jupiter and Neptune. More precisely, all 4 giants, but Jupiter and Neptune do most of the work. In the years around 2005, a group of planetary scientists, Alessandro Morbidelli, Harold Levison, Rodney Gomes, Cleomenes Tsiganis, published, in the journal Nature, a set of 3 papers now known as the NICE model of the solar system's formation. The name comes from the French city where the group worked. The Nice model tells this story. 4.5 billion years ago, when the planets had only just settled, they were not in the orbits they now occupy. Jupiter was a little closer to the Sun. Saturn was significantly closer. Uranus and Neptune were closer, and Neptune was closer than Uranus. Around and between the planets there stretched a disk of small material, icy fragments, dust, planetesimals. Estimated mass of that disk was around 35 to 50 Earth masses. Jupiter and Saturn slowly moved along their orbits. After several 100 million years, their orbital periods entered a 2-to-1 resonance, Jupiter completing 2 revolutions around the Sun for every one of Saturn's. Resonance is what happens when 2 planets keep meeting in the same relative geometry, and their gravitational interactions accumulate rather than cancel. Entering the 2-to-1 resonance was a dramatic event. It sharply disturbed the orbits of Uranus and Neptune. Neptune was thrown outward, past Uranus, and plowed straight into the disk of icy fragments. The fragments went in every direction. Some of them ended up on short-period orbits inside the planetary region, that is, the Kuiper Belt as we see it now. Some ended up on very elongated orbits that slowly evolved into the scattered disk. Some were caught by Jupiter and Saturn and thrown far outside, tens of thousands of astronomical units. Out there, over millions of years, passing stars and the tides of the galaxy rounded them into a spherical distribution. That became the Oort Cloud. The Nice model explains a lot. It explains why the surface of the Moon and of Mercury still carries the scars of an intense late bombardment about 4 to 3.5 billion years ago. That is a consequence of the same planetary rearrangement. During the migration of the giants, huge amounts of debris were thrown inward, and part of that debris fell on the Moon and the inner planets. That event is called the Late Heavy Bombardment. Some scientists today question whether the Late Heavy Bombardment was really a single event, or whether the bombardment rate was in a smooth, gradual decline from the solar system's very beginning. New data, better dating of returned moon samples, the Bepi-Colombo mission to Mercury, future sample returns from asteroids, is being gathered slowly. But for our subject, the main point stands. The same wave of giant planet migration that caused the Late Heavy Bombardment is also the wave that populated the Oort Cloud. Both are consequences of the same event. The icy chunks that now drift slowly at 70,000 astronomical units from the Sun are cousins of the debris that fell on the Moon and gave it the face it wears today. The Nice model also explains why so many bodies in the Kuiper Belt, the scattered disk, and the Oort have the same chemistry. They were all thrown out of one common source disk. And it explains why the Oort's total mass today, roughly 40 Earth masses by best estimate, is much smaller than the mass of the source disk it was populated from. Over 4.5 billion years, 3/4 or more of the original population has already been lost. Passing stars and galactic tides have driven the outer bodies away. The Oort has been slowly eroding for its entire life. We are catching it well after its early crowded youth. But the same forces that unbind bodies outward can also nudge others inward. And sometimes, out in the inner cloud, an object catches such a nudge and begins its long fall toward the Sun. One of them is falling right now. We will see it in a few hundred years. The stories of its relatives that already made it in are the next part. 23rd of July, 1995. 2 men who have never met each other in the same night look through different telescopes in different American states, and each of them sees the same tiny, fuzzy point of light. Alan Hale is sitting on the driveway of his home in Cloudcroft, New Mexico. He has a private telescope, a reflector with a 40-centimeter mirror. Hale is a professional astronomer with a doctorate in solar-type stars. He came outside to look at comet Klemola-Pajowski, which colleagues are tracking. He aims his telescope at the region where that comet should be, and out of the corner of his eye, he notices that somewhere at the edge of his field of view, in another part of the sky, in the constellation Sagittarius, near the star cluster M70, there is another faint smudge. He checks the catalogs. Nothing in that position matches. He looks for a while. The smudge does not move relative to the stars over the course of an hour, but it is there. Hale writes down the date, the time, the coordinates, and an estimate of the brightness, around magnitude 11. He sends an email to the Minor Planet Center, the office that centrally receives new comet and asteroid discoveries. The same night, 2.5 hours to the west, in Stanfield, Arizona, Thomas Bopp is looking through his friend's telescope. Bopp does not own a telescope of his own. He is 45, works as a manager at a building materials company, has a wife and children. Astronomy has been his passion since youth. The friend has brought his own homemade 17-inch Newtonian Dobsonian out into the desert to look at deep sky objects. Bopp came along. The friend aims at cluster M70. Bopp looks into the eyepiece, and, again out of the corner of his eye, he notices, near the cluster, a faint smudge of light. He asks his friend what it is. His friend does not know. They check the star atlas. Nothing is charted there. Bopp sketches by hand the position of the smudge relative to the surrounding stars. He drives home overnight. In the morning at work, he borrows a piece of telegram paper from the office secretary, and he sends a telegram to the Minor Planet Center with a description, coordinates, and date. Both reports reach the center on Monday. Daniel Green, the officer in charge, cross-checks them. They match. He verifies against fresh images. There is indeed a new comet where both men said it should be. Nothing catalogued matches. The comet is assigned the temporary designation C1995-01, and the official name, jointly by the co-discoverers, filed almost simultaneously, Hale-Bopp. That is normal in the comet world. 2 or more people independently spotting the same object often get a joint name. Comets are rare in the sky, but each large one has a specific discoverer, often an amateur. Bopp was an amateur until that night. From then on, he was in the history books. What was strange about Hale-Bopp is that it had been spotted 2.5 years before its closest approach to the Sun. Ordinary comets grow bright only near perihelion, over a few weeks or months. This one was noticed while it was still at 7 astronomical units from the Sun, roughly out near Jupiter's orbit. That could mean only one thing. The comet was huge. Later observations confirmed it. Hale-Bopp's nucleus was estimated at 40 to 80 kilometers across. For comparison, Halley's comet has a nucleus of about 15 kilometers. Hyakutake, observed in 1996, had a nucleus of about 4 kilometers. Hale-Bopp was many times larger than almost any known long-period comet. For a year and a half, the world watched it come in. Each month it grew brighter. Each month a new, short newspaper item was written. Hale-Bopp had been preceded, in the spring of 1996, by Hyakutake, which was itself an Oort Cloud comet, and which passed closer to the Earth than any comet in 2 centuries. There had already been a lot of noise around Hyakutake. Hale-Bopp made even more. 1st of April, 1997. Comet Hale-Bopp reaches its perihelion. Its closest distance to the Sun is 0.914 astronomical units, just slightly under the Earth-Sun distance. It never comes close to the Earth itself. The minimum approach, at the end of March, was about 1 3/10 astronomical units, which is roughly one more Earth orbit of distance between us and the comet. And still, for 18 months in a row, it was visible with the naked eye. That is an absolute record for known comets. Comets are normally bright for days, weeks, occasionally a couple of months. Hale-Bopp glowed in the sky for a year and a half. From May of 96 through December of 97. It was best seen in the northern hemisphere in the spring of 97, with 2 distinct tails going in different directions. One tail, bluish, thin, straight, the ion tail, always pointing away from the Sun. The other tail, whitish-yellow, wide, gently curved, the dust tail, trailing behind the comet along its orbit. If you were alive in the Northern Hemisphere in 1997 and ever went outside in the evening, you saw it. It was brighter than every star in the sky except Sirius. Even from cities where light pollution normally hides the stars, Hale-Bopp came through. So what is a comet actually, if we take it apart? The nucleus is a lump of ice a few kilometers across, for Hale-Bopp, a few tens of kilometers. By spectral analysis, its composition is water ice, carbon dioxide, carbon monoxide, methane, ammonia, methanol, formaldehyde, hydrogen cyanide, hydrocarbons, dust. A mixture of ice with a lot of complex chemistry, pressed together over billions of years of cold. Density of a typical cometary nucleus is about half the density of water. That is, a comet would float on water, if it could ever meet any. While the nucleus is far from the sun, it stays frozen and dark. No glow, just a cold lump on its trajectory. When it comes closer to the sun, from 4 or 5 astronomical units inward, the ice on its surface starts to sublime. Sublimation means going straight from solid to gas, skipping the liquid state. Around the nucleus, a coma forms, a gas and dust envelope. It can be tens of thousands, hundreds of thousands, or in the biggest cases over 1 million kilometers wide. Hale-Bopp's coma at its peak was around 2.5 million kilometers in diameter, more than 8 suns across. The coma is thousands of times brighter than the nucleus itself because it scatters sunlight in every direction. It is because of the coma, not the nucleus, that comets become visible from very far away. Behind the coma come the tails, 2 of them. One is the ion tail. The gas atoms of the coma get ionized by ultraviolet from the sun and by the solar wind, losing electrons. The ions are then caught by the magnetic field of the solar wind and dragged away, straight away from the sun, regardless of where the comet itself is heading. The ion tail is thin, bluish. The color comes from the emission of ionized carbon monoxide. Hale-Bopp's ion tail reached tens of millions of kilometers at its peak. The second tail is the dust tail. Dust that came off the nucleus with the subliming ice is pushed on by 2 forces: the sun's gravity, which pulls it back, and the pressure of sunlight, which pushes it outward. The balance between those 2 forces is different for different particle sizes, and so the dust tail comes out broad, curved, drawn along the comet's path. Hale-Bopp's dust tail was distinctly yellow-white and noticeably wider than the ion tail. The coma only lives while the comet is close to the sun. Once the comet moves back out, sublimation slows, the coma fades, the tail shortens, and the comet returns to being a cold, dark lump. Hale-Bopp's coma was faintly detectable in telescopes until about 2011. For 15 years after peak, it kept losing gas slowly. Then, it fell fully quiet. What happened to Hale-Bopp next? It went back out. Its orbit, worked out with great care from the observations of 95 through 97, has a period of about 2,530 years. That is less than it should have been if the comet had stayed on its original Oort orbit. In 1996, 1 year before perihelion, the comet passed close to Jupiter. Not critically close, about 770 million kilometers. But Jupiter's gravity slowed it down slightly and pulled it onto an orbit with a smaller aphelion than before. Before that Jupiter encounter, its period was over 4,500 years. After, 2,500. Which means the next visible return is around the year 4,527. Not us. Not our grandchildren. More than 100 generations of humanity from now, if humanity is still there. It is now moving away from the sun at about 5 kilometers per second. By best estimate, in 2025, it sits at 55 to 60 astronomical units from the sun, already past Pluto, drifting through the scattered disk, gradually working its way back toward the Oort. Hale-Bopp was not alone. Over the last 30 years, we have seen a handful of bright, long-period comets come in from the Oort. Hyakutake. Discovered on the 30th of January, 1996, by the Japanese amateur Yuji Hyakutake with binoculars. Small nucleus, about 4 kilometers, but it passed very close to the Earth, closer than 1/10 of an astronomical unit. It was the brightest comet in 20 years, until Hale-Bopp. Its period before Jupiter perturbed it was thousands of years. After the perturbation, about 70,000, which means its next return will be around the year 72,000. Ikea Seki, 1965. It grazed the Sun by 450,000 kilometers, deep inside the corona. At perihelion, it was bright enough to be seen with the naked eye during daylight, right next to the Sun. Neowise. Discovered in March 2020 by the automated infrared telescope of the same name. Well observed in the summer of 2020, in the middle of the pandemic, which made it especially memorable to amateurs. Its period is about 6,800 years. Its previous inbound pass came during the time when the first cities of Mesopotamia had only just risen, and when Egypt did not yet have its pyramids. Its next return will fall around the year 8,820. Comet Donati, of 1858, deserves a mention because it lived just before the age of astrophotography. Italian astronomer Giovanni Donati and others sketched it by hand. It was so bright that painters of the time drew it over Paris while a full moon was still up. Its period was about 2,000 years. Then there is West of 1975 and 96, sometimes called the Great Comet of 76 because it appeared with 2 clear tails, easily visible with the naked eye. It broke into 4 fragments at perihelion. Its offspring are still on its orbit. Some of them may one day return as separate, smaller comets. Tsuchinshan Atlas. C. 2023, A3. Discovered in January of 2023 by the Purple Mountain Observatory in China and by the Atlas survey simultaneously. It reached perihelion on the 27th of September, 2024. In mid to late October of that year, it was visible from the northern hemisphere. Its period is estimated at around 80,000 years, if it returns at all, because its close passage to the Sun and Jupiter may have added enough speed to send it on a hyperbolic escape trajectory, in which case it is now leaving the solar system forever. And separately, Bernardinelli Bernstein. Discovered, as we said earlier, in 2021. 140-kilometer nucleus, the largest known. It will reach perihelion in January 2031 at 10.9 astronomical units, beyond Saturn. It will not become a naked-eye comet. Nobody will see it with the unaided eye. Its importance is different. It is the first time we have caught such a large Oort body early enough to observe it in every detail for a full decade before perihelion. We already know its chemistry, its shape, its rotation rate, and dozens of telescopes have their observing time reserved on it for the years ahead. And that is only the ones already on their way in, or nearly here. Somewhere out there right now, at 50 or 100,000 astronomical units from the Sun, another body has just received a small gravitational nudge from a passing star or from the tides of the Milky Way. Its orbit has shifted a little. Its perihelion, which used to be at 100,000 units, is now at 50. Over the next million years, it will begin its first plunge toward the Sun. We will see it. Not us, of course, the people who live then. But who is doing the nudging? Who exactly gives that push? How does it work? The answer came in September of 2024, and it turned out to be more beautiful than anyone expected. 21st of September, 2024, New York City, the Upper West Side, the American Museum of Natural History. In the basement wing of the museum stands the Hayden Planetarium, a round dome 20 meters across, 429 seats, an enormous projector that shows not stars and not cartoons, but direct visualizations of data from telescopes and supercomputers. During the day, the planetarium fills with school groups. In the evening, there are science lectures. On Saturday mornings, there are open discussions for people who follow astronomy. In September of that year, the team behind the finding was reviewing on the Great Dome a simulation from the Pleiades supercomputer at NASA, a calculation of how the Oort Cloud looks under the influence of the galactic tide over billions of years. The simulation was run by David Nesvorny, a Czech-American planetary scientist at the Southwest Research Institute in Boulder, Colorado. He is one of the leading specialists on outer solar system dynamics, the Nice model, the Kuiper Belt, the scattered disk, the way they evolved. The task was a technical one. Take an initial distribution of 100 million virtual icy bodies scattered around the Sun at distances from 2,000 to 100,000 astronomical units. Give them slow motion along stretched orbits, like real Oort bodies, and run the system forward for 4.5 billion years under every known external force: gravitational tugs from passing stars, tidal forces from the Milky Way, occasional passages through giant molecular clouds. The calculation took 5 months on the supercomputer. By September of 2024, it was ready. Jackie Faherty is an astrophysicist, a senior scientist at the museum, a specialist in low-mass stars and brown dwarfs, with a strong interest in the outer solar system. She curates several public-facing research programs, and she is often the first person to view new simulations from her colleagues because she has to decide how to visualize them for the public. That Saturday, she asked the operators to project the Nesvorny simulation on the Big Dome. She and colleagues wanted to see, at last, how 100 million particles behave under only external forces around the Sun. On a flat screen, the simulation looked like a diffuse cloud of dots, nothing special. It looked the same as on every other run before, just points, spherically distributed. The Hayden Planetarium dome is three-dimensional. The projector displays the image so that a viewer, leaning back in the seat, does not see a picture but a volume. Depth is real, and the brain reads it correctly. Viewed that way, the simulation showed something that had not been noticed on flat screens. Among the spherical scatter of points, there was a structure, not a sphere and not a disk. Two broad, curved bands wrapping the Sun through the inner part of the cloud, like two arms of a spiral galaxy, a small, local one, tucked inside the Oort itself. Replayed from different angles, the bands never went away. They were in the cloud. By coordinates, she saw that the arms formed at roughly 15,000 astronomical units from the Sun. That is deep inside the cloud, in the region that by Hill's classification belongs to the inner cloud. And the arms did not lie in the plane of the planetary system, nor in the plane of the galaxy. They stood almost perpendicular to the galactic plane. The shape, a two-armed spiral, like a small, self-contained pinwheel embedded in the outer wilderness of the solar system. Because the same simulation had been run many times before, always on flat screens where the structure gets lost in the fuzzy background of the sphere, the finding took some persuasion. The immersive projection was what had revealed it. From that point, the long work began. Confirm that the structure is real and not a visualization artifact. Confirm that it does not depend on the initial conditions. Understand what physical phenomenon produces it. In February of 2025, on the archive preprint server for physics and astronomy, a paper appeared by David Nesvorny, Luke Dones, Jackie Faherty and colleagues, titled A Spiral Structure in the Inner Oort Cloud. Their conclusion: the spiral is a robust feature of the simulation, and it emerges over billions of years from the long, steady action of the tidal gravity of the Milky Way on the orbits of inner Oort bodies. What that means, in plain language: the Milky Way is not a uniform blob of mass around the Sun. Different sides of the solar system are pulled by slightly different amounts. Over a single orbit, that tiny difference is negligible. Over hundreds of millions of years and thousands of orbits, it slowly reshapes the inner cloud, twisting a fraction of its bodies into two long, curved arms. Not rigid, not dense, thin, layered over the main spherical distribution, but geometrically real. For the first time in the 75 years since Oort's hypothesis, simulations have given us a specific, testable prediction for structure within the inner Oort Cloud. From 1950 until this new work, we imagined the Oort in general terms: spherical, loosely structured, population around 1 trillion bodies. Simulations had long shown that it should evolve under external perturbations. What had not been done before was to identify a specific, drawable structure in one of those simulations. This model turns out to contain one. Inside the sphere, the simulation resolves a spiral, thin, like the trace of a slug in a pond, but geometrically clear. If a spiral like this exists in the real inner Oort cloud, it could influence the directions and rates at which bodies are perturbed onto cometary orbits. Future surveys may test whether that predicted structure leaves any observable signature in the orbits of long-period comets, in the arrival pattern of showers, or in the properties of newly discovered inner Oort objects. Verification of the spiral is the work of the next decade. And here another main character of this film enters: the Vera Rubin Observatory. But before we get to Rubin, one debt to the Oort. We have to name concretely who is nudging the bodies in the spiral and in the rest of the cloud. We have already said in passing stars, and the tides of the galaxy. Now we can name them: passing stars. The solar system is moving through the Milky Way at about 220 kilometers per second. Over 1 billion years it sweeps through large volumes of the galactic disk. Estimates suggest that in each million years, about 13 stars pass within 1 parsec of the Sun, within 3.5 light years. Of those, about 1 every 100,000 years passes within 50,000 astronomical units, deep inside the outer Oort. Each such passage kicks the cloud. Usually the kick is weak, the star is far away, and gravity falls off with the square of distance. But some passages are very close, and those kicks are strong. Some bodies are unbound and drift out into interstellar space. Others begin to fall inward. One such passage we discovered in hindsight. The star WISE 0720-0846, spotted in 2013 by the WISE infrared telescope and informally called Schultz's star after its discoverer, is a faint red dwarf paired with a brown dwarf, currently about 22 light-years from the Sun. Backtracing its trajectory shows that about 70,000 years ago, the pair passed within 0.82 of a light-year of us, about 52,000 astronomical units. That is inside the outer Oort. What perturbations it caused is not yet clear. Its mass is only 8% of the Sun's, so the kick was modest. Some of the comets falling toward us today may have been nudged loose by Schultz 70,000 years ago. We cannot prove it for any individual comet, because we cannot compute a comet's orbit backward over that long a time with enough accuracy. One passage is already predicted for the future. Gliese 710, a faint orange dwarf, currently at 62 light-years from us in the constellation Serpens. According to data from the Gaia Space Telescope, it is approaching the Sun and will make its closest approach in about 1,290,000 years. Closest distance, about 13,000 astronomical units. Deep inside the outer Oort, on the edge of the Hills cloud. That will be the closest known stellar passage past the Sun for the whole geological time span. What it will do to the cloud, from simulations, is unbind a significant fraction of the inner cloud from their orbits. Some will fly outward, some will fall inward. Over several million years afterwards, a large flow of long-period comets will fall toward the solar system, a comet shower. Neither we nor anyone from our lifetime will see it. Not because humanity would not. If it survives that long, perhaps it will, and perhaps by then it will still be doing astronomy. Simply because we, personally, will not be there in 1,290,000 years. Galactic tides. This is the other mechanism, and it works continuously, not in single events. The Milky Way is a large mass, and the mass is not uniformly distributed. Different sides of the solar system are pulled by different amounts. That difference in pull is the tidal force. It is small, much smaller than the sun's own gravity, but it acts without stopping, billion of years after billion. Over 4.5 billion years, the galactic tide has stripped a huge fraction of the outer Oort simply by accelerating certain bodies past the solar escape velocity. That same tide gently pulls the outermost bound bodies inward and quietly delivers us the rare, long-period comets we see. And, in combination with the Kozai-Lidov mechanism, it gave the inner cloud its two-armed spiral shape. Two continuous forces, the tides of the galaxy, and on longer intervals, passing stars, plus the occasional passage of a giant molecular cloud, together turn the Oort into something that is not a static reservoir, but a slowly living, eroding, breathing structure. A trillion bodies out there wait for their nudges. Every century, some fraction gets one. Some become the comets we photograph. Some pass by unseen and go back out. And every million years or so, one or two large bodies actually manage to disturb a planet, the Earth or Jupiter included. The Nemesis hypothesis, the invisible stellar companion, is almost never taken seriously today. Not only because Nemesis was never found, also because there are now more economical explanations for cometary periodicity, galactic tides, and the spiral of the inner cloud they carve out over billions of years. The two-armed spiral of September 2024 is a beautiful, simple, physically clean explanation for what people used to blame on a mythical evil twin of the sun. And if Proxima has a cloud like ours, it is already touching ours. That is the next part. In part 1, we sketched the three edges of the solar system: heliopause at about 120 astronomical units, farthest known orbit near 1,000, and the gravitational Hill sphere at 100 to 200,000. Between them, factors of 1,000. Between those three edges lives the Oort Cloud. Inner edge, 2 to 5,000 units. Outer edge, 100 to 200,000. It fills nearly all of the sun's gravitational domain, from the Kuiper region out to the Hill sphere. The practical answer to where does the solar system end sounds like this. The solar system ends where the sun stops being the gravitational master. That is the radius of the Hill sphere. And that radius is not a sharp line, but a fuzzy gradient. Nearer the Hill sphere, the bodies feel the sun less and less, and other stars more and more. The outer edge of the Oort cloud is not a fence. It is a zone where the sun gradually hands off to the galaxy. Between that zone and us, there are more than 100,000 astronomical units of vacuum, populated by isolated icy chunks separated on average by tens of millions of kilometers. The density of matter in the Oort is less than that of the best laboratory vacuum on the Earth. If you were standing somewhere in the middle of the Oort cloud and you wanted to spot the nearest neighboring chunk, you would need a very powerful telescope. And even with one, that chunk would appear as a faint smudge somewhere near the limit of detection. The Oort is not a shell. It is not a thick donut of comets wrapped around the sun, the way it is sometimes drawn in popular pieces. It is a sphere in which, on average, a volume the size of the Earth contains only a fraction of a single small body. 1 trillion bodies spread over a sphere 4 light-years wide is a monstrously thin medium. That is why the Oort can hold trillions of bodies and still look almost like pure vacuum. That is why Voyager 1 will pass all the way through it without a single encounter with anything noticeable. And that is why we have never seen a single Oort body in place. They are simply too far apart to form observable clumps. Now, the question that has been sitting in the comments of nearly every film like this one: are there Oort clouds around other stars? Similar comet reservoirs are expected around many other planetary systems, although we have not yet directly observed a foreign Oort cloud around any other star. There are indirect signs. First, the formation of the cloud is expected to be a natural byproduct of the birth of a planetary system with massive giant planets. Jupiter and Neptune, through their gravitational influence, scattered some of the initial material into very distant orbits. Any star that hosted big planets during its own formation is expected to have done the same thing, which means that around many such systems, there ought to be a cloud like ours. Second, we are now observing interstellar objects, bodies that came to our solar system from beyond it. 1I Oumuamua in 2017, 2I Borisov in 2019, 3I Atlas in 2025. These are, almost certainly, bodies that originally belonged to the Oort clouds of other stars, then were knocked loose by yet another passing star or by the galactic tide, and now drift free in the interstellar medium. We have detected only 3 so far, but that is only because those 3 happened to enter a part of the sky where our surveys were watching. Total interstellar icy bodies must be many, because every star continuously loses residence from its own cloud. Third, some of the bodies that today populate our Oort cloud may have been captured by the Sun from other stars in the Sun's infancy. Simulations from the 2010s onward, including work by Haley Gilbert and Scott Tremaine at the Institute for Advanced Study in Princeton, showed that in its first few 100 million years, the Sun lived inside a dense stellar cluster, where stars were packed much closer than they are today. In such close quarters, Oort clouds of neighboring stars would have overlapped, and bodies could migrate between them. Some of the objects in our outer cloud may have been born around other stars. Simon Portuguese Zwart of Leiden University in 2025 developed this idea further. By his model, a substantial fraction of the outer Oort cloud's mass may consist of bodies originally formed around other stars of the Sun's birth cluster, captured by the Sun when the cluster dispersed. If that model is right, our cloud is not entirely our own. It would be populated in part by immigrants from neighboring systems. This remains a specific modeling result, not an established fact. Fourth, and the most interesting for practical purposes. If Proxima Centauri, the closest star to us, has its own Oort cloud, it may very well be touching ours. Proxima sits at 4¼ light years. Our Hill sphere is about 1 parsec, 3¼ light years. If Proxima has a similar Hill sphere, which is plausible since its mass is only about 8 times smaller than the Sun's, so its Hill sphere should be about half of ours, then the total sum of our Hill spheres does not quite meet. But the outer, weakened edges of our clouds, the transition zones, very likely overlap. In any case, between the Sun and Proxima, there is no sharply empty gap. There is a gradient, in which our icy chunks and hers slowly interleave. Isotope ratios, D/H, the ratio of heavy hydrogen to ordinary hydrogen, have now been measured in several dozen comets. Some of them have ratios close to the Earth's oceans, some noticeably higher, some lower. Those differences may reflect that comets formed in different regions of the original solar system disk, or they may reflect that some of them came to us from other stars, where the D/H was different. Isotope ratios have become a key line of evidence in the question of where the Earth's water came from. In 2014, the European Rosetta probe, operating at the nucleus of comet 67P Churyumov-Gerasimenko, measured its D/H ratio and found it 3 times higher than in the Earth's oceans. That meant that Jupiter family comets, the short-period ones coming from the Kuiper Belt, could not have been the main source of our water, which means the water came from asteroids or from another family of comets, possibly the Oort ones, with D/H closer to the Earth. The panspermia hypothesis, the idea that not only water, but the first primitive organic chemistry was delivered to the Earth by comets and asteroids, is also linked to the Oort. Molecules found in Hyakutake, Hale-Bopp, 67P, and others, methanol, formaldehyde, hydrogen cyanide, the amino acid glycine, could, under the right conditions, have been building blocks for longer organic chains. Whether the Oort is really the source of our water and our first chemistry is an open question, but indirect evidence points that way. Between us and other stars there is no empty space. there is a fuzzy border. Our cloud does not end abruptly. Proxima's cloud does not end abruptly. In between, there is a transitional zone where neither is dominant. And in that zone, quiet, icy bodies live, and over 1,000,000 years, some of them slide from one gravitational realm into another, without us ever knowing about it. The good news is that in 2026, an instrument comes online that, for the first time in history, may let us look into the Oort Cloud not through comets, but directly. The Vera C. Rubin Observatory on Cerro Pachón in Chile, an 8-meter mirror, a camera of 3 2/10 gigapixels, a survey of the entire southern sky every 3 nights for 10 years running. And on its target list are hundreds of new inner Oort objects, the Nesvorny-Faherty spiral, the hypothetical Planet 9, and the older stellar siblings of the Sun from its birth cluster. If any of it exists, Rubin will see it. In 2026, for the first time in history, one instrument will be able to test all of this directly. Coquimbo region, northern Chile. The Pachón and Tololo ridges, 2 neighboring peaks in the dry Atacama Desert, where the nights year after year stay clear, the humidity is almost 0, and atmospheric turbulence is among the lowest on the Earth. Here, 50 kilometers from the nearest town, the most sensitive telescopes in the world get built. Here operate the Tololo Observatory, Gemini South, SOAR. And in the past few years, the instrument that ought to reshape the next 2 decades of astronomy, the Vera C. Rubin Observatory. It is named after the American astronomer Vera Rubin, the one who in the 1960s and 70s measured the rotation speeds of spiral galaxies and found that they were spinning as if they contained many times more mass than could be seen. That was the first direct observational evidence for dark matter. Rubin died in 2016 without ever winning a Nobel Prize, though many think she was the leading candidate for that discovery. The observatory was renamed in her honor in 2019, deservedly. Construction began in 2015. The dome was installed in 2020. The 8-meter primary mirror was delivered in 2021. The 3 2/10 gigapixel camera, the largest digital camera in the world, was assembled at SLAC in California and delivered to Chile in 2024. First light, the first official on-sky image, took place on the 23rd of June, 2025. The main survey, called the Legacy Survey of Space and Time, or LSST, begins in 2026. What makes the Rubin Observatory special, given that we already have big telescopes, the same Gemini South next door, Keck on Hawaii with its 10-meter mirrors, the Very Large Telescope in Chilean Paranal with its 4 8-meter modules? The answer is not mirror size. Rubin's mirror is 8.4 meters, not a record. The distinction is in the design. Rubin is not just a big mirror telescope. It is a telescope built specifically for wide field imaging over a very large sky area, with very high sensitivity, many times over a short interval. A classical large telescope has a narrow field of view, about 1/10 of a degree. It takes a very detailed picture of a small patch of sky. One image is a lot of data, but only about that small patch. To sweep across the entire sky, you would need tens of thousands of images and years of observing time. Rubin has a field of view of 9 6/10 square degrees. About 40 full moons fit into a single image. In one 15-second exposure, it captures 500 times more sky than a classical big telescope in the same time. And its camera, at 3 2/10 gigapixels, means that each pixel sees a small piece of sky, and a single image contains as much data as about 3,000 HD photographs. That allows it to sweep across the entire southern sky visible from its latitude, about 18,000 square degrees in 3 nights. And to keep doing that, over and over, for 10 years. By the end of the survey, we will have about 800 images of each point in the southern sky, taken in 6 different filters at different moments in time. The final dataset will be around 60 billion astronomical objects. That is, roughly 10 times more than the total number of objects known in all optical catalogs today combined. What does that do for the Oort Cloud? The most direct thing, a survey of small, distant, moving objects. Every Kuiper Belt object, every scattered disk object, every inner Oort object, if it is large and not too far, moves across the sky at a small but detectable rate. Slowly. But over 3 or 4 nights between successive Rubin images, the shift is measurable. The pipeline automatically flags every moving point and sends it into the catalog. Over 10 years, the survey should discover somewhere between hundreds of thousands and a few million new outer solar system objects. Of those, hundreds are expected to be new detached and inner Oort candidates, the class currently represented by Sedna, 2012 VP113, Leleakuhonua, Far Far Out, and a small number of other well-characterized objects. Rubin could transform that population from a few tens of known members into something with enough statistics to test models against. What does that give us? On the statistical side, we go from a small number of well-established inner Oort candidates today to hundreds within a decade. With that many, a real distribution can begin to be built. How they are spread across orbital parameters, whether there are preferred inclinations, whether there are traces of the Nesvorny-Faherty spiral, whether the extreme orbit clustering that gave rise to the Planet 9 idea is real or a small sample artifact. By around 2030, Rubin should place some of the strongest observational constraints yet on the Planet 9 hypothesis, and could discover the planet outright if it lies within the survey's accessible region. And if the spiral is really stamped into the inner Oort distribution, we will end up, for the first time in history, with a real map of at least part of the cloud rather than only a simulation. On the moving object side, Rubin will pick up incoming comets decades before they reach the Sun. As soon as one rises above the sensitivity threshold, it enters the catalog, and we gain years of warning to prepare instruments, and even the option of sending a probe to meet a big Oort comet long before perihelion. Over the same 10 years, several dozen new interstellar visitors like Oumuamua and Borisov are expected. Each one is a specimen from a foreign stellar system handed to us, and the more we get, the more we learn about the diversity of Oort clouds across the galaxy. And separately from the Oort work, one of Rubin's core missions is to complete the census of Earth-crossing asteroids larger than 140 meters. Today we know about a third of them. Rubin should close the gap almost fully by the end of the survey. A word or two separately about the camera itself. It is called the LSST camera, and it was assembled at the SLAC Linear Accelerator in California. At the time of construction, the largest digital camera in the world. Its diameter is 1/6500ths of a meter. Its mass is 3 tons. Its sensor is a mosaic of 189 separate CCD arrays, each of 16 megapixels, tiled together. Each sensor is cooled to -100 degrees Celsius, because at ordinary temperatures the thermal noise would swallow the faint signal from distant objects. A single exposure lasts 15 seconds. During that time, each point of the sensor accumulates photons from a specific direction. Then the sensors are read out, the image is written to the disk system, the telescope slews to a new field, that slew takes 5 seconds, and the next exposure begins. Over a night, roughly 1,000 exposures are taken, about 20 terabytes of data per night, around 500 petabytes of raw data over the 10 years of the survey. Data reduction is a project of comparable scale. Every image is automatically compared to previous exposures of the same field. Anything that moves or that changes brightness is flagged and sent into a special data stream. Rubin is expected to generate about 10 million alerts per night, messages about new or changed objects. Broker systems worldwide will distribute those alerts to science teams. Astronomers will get notifications about new supernova, new comets, new asteroids, new quasars, within 60 seconds of the last photon hitting the sensor. This is a fundamentally new mode of astronomy. Until now, big surveys took a long time to run, and the analysis of their data took years. Rubin will produce and distribute discoveries almost in real time. That is especially important for the Oort, because when Rubin spots a new inner Oort body, and these bodies move very slowly across the sky, so the first detection typically gives a poor orbit. The orbit can only be refined if several different observatories with different telescopes pick up the observation quickly and add their own data. That kind of coordination is only possible with instant alert distribution. By 2035, the end of the survey, Rubin's catalog will hold about 60 billion objects. Of those, by different estimates, several tens to several hundreds of new Type 1a supernovae per week, about 10 million known main belt asteroids, thousands of new Kuiper Belt objects, hundreds of scattered disk and inner Oort bodies, dozens of new interstellar visitors like Oumuamua. Plus, for the first time in history, an accurate census of all large near-Earth asteroids to well under an astronomical unit. There is one separate pride the project takes in itself. All Rubin data becomes public 2 years after collection. Anyone on Earth with a computer and an internet connection will be able to search its catalogs. Surveys of this scale used to be closed almost by default. Only members of the consortium could work with the data. Rubin does it the other way. Open science, at scale. Now, Planet 9 deserves a longer paragraph. In January 2016, Konstantin Batygin and Mike Brown of the California Institute of Technology published a paper in the Astronomical Journal titled Evidence for a Distant Giant Planet in the Solar System. At that moment, 6 objects were known in the scattered disk and inner Oort region with very stretched orbits, all with perihelion beyond 30 astronomical units and semi-major axis beyond 250 units. Batygin and Brown noticed that the orbits of those 6 objects had perihelia pointing roughly toward the same region of sky, and orbital planes tilted in the same direction. The probability of chance alone, by their calculation, was less than 0.1%. Their conclusion: somewhere at very large distance from the Sun, somewhere in the range of 400 to 800 astronomical units, there ought to orbit a massive planet, mass of 5 to 10 Earths. It gravitationally binds the orbits of those 6 objects into a single bundle and pushes them all in the same direction. No other explanation for such a clustering, other than a massive unseen body, could they find. The planet was named Planet 9, as a running number after the 8 known planets. Since then, it has been searched for on all major telescopes. Not yet found. There are 2 possible reasons. Either it does not exist, and the clustering of those 6 orbits is explainable by the small sample size, because we have found only a few objects out there and by luck picked 6 similar orbits. Or it does exist, but it happens to be in a part of the sky that no big survey has yet swept carefully. Estimates say that if it exists at the mass Batygin and Brown propose, it should be within reach of telescopes like Subaru or Rubin, bright enough for their sensitivity. Rubin, observing the southern sky, will cover most of the plausible parts of sky for Planet 9. By 2030, if the planet exists and is in the accessible zone, Rubin will find and confirm it. If it does not, the case for Planet 9 will weaken considerably, and alternative explanations will take more ground, such as a recently proposed picture in which the clustering is caused by a ring of small bodies on similar orbits rather than by a single big planet. Or the possibility that the 6 similar orbits were themselves a product of observational selection, because our telescopes searched certain regions of the sky more thoroughly than others. Another Rubin target, finding the older siblings of the Sun. The idea of stellar siblings is this: all stars, including the Sun, are born not alone but in stellar clusters. The young cluster in which the Sun was born held, by different estimates, from several hundred to several thousand stars. It lasted a short time, the first 1 to 200 million years, and then broke apart gravitationally. The stellar siblings scattered across the galaxy, and by now have moved very far from each other. They can be found in two ways. The first, by matching trajectories in the past. If the motion of stars is traced backward through galactic space, siblings should converge in the same region about 4.5 billion years ago. The second, by matching chemical composition. All stars of one cluster should have the same metallicity and the same isotope ratios, because they formed from a single cloud of gas. A few candidates have already been found, notably HD 162-826 in Hercules, HD 186-302 in Pavo, but their identification is not final. The Gaia Space Telescope, operating since 2013, has given us precise coordinates and motions for almost 2 billion stars in the Milky Way. Using its data, we can now trace trajectories backward with high accuracy. Rubin, imaging the sky in optical filters, will help measure the metallicities and colors of those candidates. Combined catalogs from Gaia and Rubin can give us the first large list of the Sun's brothers and sisters, and from them, knowing their positions, a new view on what the birth cluster of the Sun was like, where inside the galaxy exactly the Sun formed, and how far apart its companions have drifted over the intervening billions of years. What does that mean for the Oort? It means that we may finally learn where specifically some of its bodies came from. Simon Porteges-Zwart of Leiden argues that a fraction of the outer Oort cloud was captured by the Sun from other stars still within the stellar cluster. If we find the Sun's siblings and measure the chemical fingerprints of their planetary systems, we may then be able to match those with the unusual isotope signatures of some of our comets and confirm or refute the capture hypothesis. In other words, Rubin can tell us not only about the Oort, but about who the young Sun's neighbors were. In 2026, for the first time in history, we will have one instrument that can address all of these questions at once. Not separately, Planet 9 here, Oort there, Golden Record elsewhere, but with one survey, 10 years long, the whole southern sky, night after night. Voyager 1 will fall silent in 2036, but it is already carrying its golden record to somewhere no living human will ever reach. What Voyager is carrying is the next part. 1977, Pasadena, California. The Jet Propulsion Laboratory. A small office on the second floor. Two astronomers are sitting and deciding what to place inside the metal container that, in a few months, will fly away with the two Voyager twins into deep space. One of them is Carl Sagan, an astronomer at Cornell University, the most famous popular science figure of that generation. The second is Frank Drake, an astrophysicist at Cornell as well, known, among other things, for his formula estimating the number of communicating civilizations in the galaxy. A young literary editor and radio journalist named Anne Druyan, at the time Sagan's fiancée, later his wife, and co-author of all his subsequent work, joins the team. And a few more people, the artist John Lomberg, the photo researchers Wendy Gradison and Herman Eckelman of the Golden Record team, the sound engineer Timothy Ferris, the linguist Linda Salzman Sagan, Sagan's first wife. Their task, to assemble a sample of the Earth. The idea comes from the mission leadership itself. The two Voyager spacecraft, after their flybys of the outer planets, will drift into interstellar space. Neither of them will ever come back. Over hundreds of thousands of years, they will pass by different stars. Perhaps, someday, someone out there, if such someones exist at all, will find them. Or perhaps our own descendants, 1 million years from now, will return to those points in the galaxy and pick them up. Or perhaps nobody will find them. Either way, if the spacecraft is going to leave the Earth forever, let it carry something that gives a sense of where it came from. On each Voyager, it was decided to install the same golden disk, 30 centimeters across. Material, copper, plated with a thin layer of gold. The disk in a protective aluminum case. Engraved on that case Instructions for how to play the disk. A pulsar map, 14 lines, each pointing to and giving the characteristic period of one known pulsar, so that together they unambiguously fix the position of the solar system in the galaxy. A hydrogen atom diagram, showing the hydrogen atom before and after an electron spin flip, the one universal physical process that can be used as a unit of time. An instruction for extracting the sound and the pictures from the disk, how to place the stylus, at what speed to read, how to decode the signal back into images. The contents of the disk were gathered over 6 weeks by Sagan and his team. Greetings. 55 different languages, from Sumerian to modern Mandarin, from Swahili to Hindi, from Hebrew to Esperanto. The English greeting was spoken by Nicholas Sagan, Carl's 6-year-old son. Hello from the children of planet Earth. The Russian greeting was a woman's voice saying, Здравствуйте, приветствую вас. Hello, I greet you. Sounds of Earth, about 21 recordings. Wind, rain, surf, thunder, a volcano erupting, the song of a whale, sounds of African jungles, the sounds of a farm's animals, human footsteps on gravel, a baby crying, the beat of a human heart, laughter, a train, Morse code, a rocket launch, music. 27 tracks, chosen as a cross-section of the world's musical culture. Johann Sebastian Bach, 3 pieces, including Brandenburg Concerto No. 2 and a solo violin partita. Ludwig van Beethoven, the first movement of the Fifth Symphony, and the string quartet Opus 135. Igor Stravinsky, The Rite of Spring. Mozart, an aria from the Magic Flute. Chuck Berry, Johnny B. Good. Louis Armstrong, Melancholy Blues. Blind Willie Johnson, Dark was the night, cold was the ground. Plus traditional music from every inhabited continent. African initiation songs, Indonesian gamelan, Japanese shakuhachi, Aboriginal Australian songs, Peruvian pan flute, Azerbaijani balaban, Bulgarian women's choral song, Georgian polyphony, a Navajo chant. Images. 116 images, encoded as analog video signals that can be unrolled into pictures on any device capable of decoding a television waveform. A diagram of the solar system, the structure of an atom, a DNA molecule, cell division, human anatomy, a man and a woman, unclothed, standing next to a diagram of scale, children of different races, a mother with child, old people, views of the planet, oceans, mountains, deserts, forests, glaciers, cities, New York, Sitka, Oxford, Tokyo, transportation, medicine, sports, an Olympic sprinter, science, telescope, microscope, astronauts, food, structures, the Taj Mahal, the Sydney Opera House, the Great Wall. And one photograph, taken by Druyan and Sagan themselves, their first picture together, a few weeks before they became a couple. The disc was sealed in its aluminium case and mounted to the side of each of the 2 Voyagers. Nothing like that had ever been placed on any earlier human spacecraft. On the 3rd of June, 1977, 3 months before Voyager 1's launch, Anne Druyan went into Bellevue Hospital in New York and asked to be connected to an electroencephalograph. Her brain activity was to be recorded and included on the disc as one of the expressions of human nature. She was asked to think, for 1 hour, of anything she wanted. She thought about the Earth, about human history, about evolution, and, as she later admitted, about Sagan. 2 weeks after Voyager launched, she told him that she loved him. They married, and stayed married until his death in 1996. Where these disks are going. Voyager 1 is heading in the general direction of the constellation Camelopardalis. In about 40,000 years, it will pass within 1.6 light-years of the star Gliese 445, a faint red dwarf currently at 17.5 light-years from us. By that time, Gliese 445 itself will be closer to the Sun than it is now, about 3.5 light-years, inside the outer edge of our Oort cloud. Meaning, the very star Voyager is heading toward will enter our gravitational sphere before Voyager leaves it. Voyager 2 is heading toward Ross 248, another red dwarf, currently at 10.5 light-years in the constellation Andromeda. It will pass by it in about 40,000 years at 1 7/10 light-years. Neither Voyager will reach these stars. Both will fly past. Their speed is too slow to seriously approach any star in 1,000,000 years. They will drift forever among the stars of the galaxy, occasionally passing within a couple of light-years of some star. Their radioisotope power sources, plutonium-238, produced by irradiating neptunium-237 in reactors and then purified, are slowly decaying. The half-life of plutonium-238 is 87 7/10 years. The two Voyager thermoelectric generators originally produced 470 watts of power. Today they produce about 220. By 2036, the power will fall below the threshold needed to keep the radio transmitter running. The Voyagers will fall silent. After that, they will keep going. Frozen, dark, without a single signal, they will cross layer after layer of the solar system, radius after radius. Because Voyager 1 is climbing at 35 degrees above the plane of the planets, it will not plow through the Kuiper Belt itself, but past its latitudes. Past the inner edge of the Hale-Bopp cloud somewhere between the 24th and the 26th century. Through the middle of the inner Oort Cloud, somewhere around the 12,000th year. Through the outer Oort Cloud, toward the end of the 30,000th year. Out into interstellar space, around the same time. The whole time, it will pass without meeting any large object. The Oort's average density is so low that even over 30,000 years of flight, a car-sized spacecraft, with near certainty, will not collide with anything larger than a grain of dust. The Oort's icy chunks are simply far too apart. The empty space between them dominates completely. It will pass its first foreign star in about 40,000 years. Then, tens of thousands of years later, another one, and another. Drifting like that, it will move slowly around the center of the galaxy, together with the Sun, with the neighboring stars, with the trillions of Oort bodies. 225 million years for one revolution around the galactic center. Several dozen revolutions per lifetime of the galaxy. And Voyager will remain almost certainly undamaged, because the probability of colliding with something large in interstellar emptiness is extremely small. Voyager 2 is on the same kind of trajectory, along with the older pioneers and, in decades to come, New Horizons, the small fleet of drifting spacecraft we already met in Part 1. All of them, silent or nearly so, on their long, slow paths outward through a trillion icy bodies they will never touch. A few details about the Golden Record are worth adding, because they are often left out of the popular retellings. The disk is made of gold-plated copper. The plating is not for beauty. It protects the copper from space erosion. The design lifetime of the recording is about 1 billion years. Over 1 billion years, cosmic rays and micrometeoric dust will gradually damage it, but noticeably earlier than 1 billion, not really. Which means that if in 500 million years some observer happens to catch the Voyager, the disk will still be readable. The sequencing of the disk's contents was a separate design task. The greetings in 55 languages are ordered by geography, from older tongues to newer ones, from one continent to another. A special recording of about 44 seconds contains the greeting of Kurt Waldheim, then Secretary General of the United Nations. A separate recording is a message from Jimmy Carter, then President of the United States. This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. One eternal question is what would happen if the disk was found. The answer is that the probability is vanishingly small. Voyager 1 and Voyager 2 are heading into a very sparse region of the galaxy, where even on timescales of millions of years, the probability of a close encounter with a foreign stellar system is negligible. And even if such an encounter did happen, the probability of an observer being there is still smaller. And even if the observer is there, the probability that they choose and can catch a piece of drifting aluminium is smaller still. But the disk was not made in the hope of being found. It was made to live with the idea that we sent it, in a possible register, as a cultural gesture, not a realistic contact attempt. Sagan understood this better than anyone. He said in various interviews that the golden record was a message in a bottle thrown into the ocean. Nobody writes such a message expecting an answer. You write it because it is important to write. The same gesture explains a few other small details of the mission. The protective aluminium case of the golden record itself carries the engraving, the pulsar map of the solar system, the hydrogen atom diagram as a universal unit of time, and the detailed instructions for extracting the sound and pictures. There are no other inscriptions on Voyager. Unlike the Pioneer plaques, which carried a picture of a man and a woman, the Voyagers do not carry that kind of image, just the disk and its cover. Meanwhile, in the opposite direction, something is coming to us from the Oort clouds of other stars. The first visitor was one Oumuamua, discovered on the 19th of October, 2017, by the automated Pan-STARRS telescope on Mount Haleakala in Hawaii. The name, Oumuamua, a Hawaiian word meaning roughly the first messenger from far away. The object was on a hyperbolic trajectory. Its speed was too high for the sun to hold it, which means it did not belong to us. It came from outside. It flew through the inner solar system in a few months, and then left the other side. Its size, variously estimated from 100 to 800 meters long. Its shape, elongated, like a cigar, length to width ratio roughly 6:1. Nothing among our known asteroids or comets looked like that. It was not really a comet in the ordinary sense, no visible tail, and it was not an ordinary asteroid. It had a small, non-gravitational acceleration, which is usually explained by outgassing, but no gas was detected. Many hypotheses exist about what it could have been. An exotic type of comet with a weak tail. A fragment of a destroyed planet from another system. The hypothesis of an artificial origin has not been ruled out, but has stayed a hypothesis, without evidence, and is not accepted by most astronomers. The second visitor was 2I Borisov. Discovered on the 30th of August, 2019, by an amateur astronomer from Crimea, Gennady Borisov, working on a self-built 50-centimeter telescope. Also, a hyperbolic trajectory. Also came from outside. Also passed through the inner solar system and left. But this was clearly a comet, with a nucleus about 1 kilometer across, a gas tail, ordinary cometary chemistry. Almost no difference in composition from our own comets. It looked like a perfectly normal Oort body, only from another star's cloud. The third visitor is 3I Atlas. Discovered on the 1st of July, 2025, by the Atlas system in Chile. Nucleus about 1 kilometer across, also hyperbolic. It will reach perihelion in October 2025. By estimate, the age of this body is around 7 billion years, that is, older than our own solar system. Which means it was born around a star that has either died or turned into a white dwarf, and has been drifting in interstellar space ever since. Observations by the infrared telescope SphereX in December 2025 detected in its coma water, carbon dioxide, and complex organic chemistry. 3 visitors in 8 years. Before that, we had seen none. The Vera Rubin Observatory, from 2026, is expected to detect another 10 to 30 such objects over its 10-year survey. Each of them is a message from a foreign Oort cloud, hand-delivered. We do not know from which specific system. We do not know how many thousands or millions of years they had been traveling. We simply catch their passage and get 1 or 2 months to look at the composition of their surfaces through our spectrometers. Our clouds are permeable in both directions. We lose bodies into interstellar space. We receive foreign bodies as visitors. Between the stars, there is a slow, constant exchange of icy chunks, going on since the very birth of the galaxy. Voyager, silent since 2036, is one of our messengers in that exchange. The first one built by human hands. Silent, but with its golden record on the side. It is going where none of us will follow. And it is carrying what we decided about ourselves that September of '77, when it was still unclear what we were sending and to whom. Everything else that is left to say about the final scene, about Hale-Bopp on her long return arc, about a nameless icy chunk at 70,000 astronomical units, is the next and last part. Let us aim the mental camera at a very distant point. 70,000 astronomical units from the Sun. 1,000 astronomical units is roughly Sedna at aphelion. This is 70 times farther out. At this point there is no name, no catalog number, nothing recorded. Bodies at 70,000 astronomical units, if they are smaller than 20 or 30 kilometers, are invisible today to even the most sensitive telescopes. We know they must be there because the mathematics requires them. But which ones exactly are there, we may not see for a very long time, if ever. Take one such body, a chunk of ice 15 kilometers across, average in size. Born 4.5 billion years ago in the original planetesimal disk of the solar system, somewhere between the orbits of Uranus and Neptune. Within a few 100 million years, gravitationally thrown out by the young Neptune, a sequence of close passages slowly stretched its orbit until its aphelion moved out to tens of thousands of astronomical units. By the end of the first billion years of the solar system, its orbit had reached its current size, an elongated ellipse with perihelion at about 3,000 astronomical units and aphelion at 70,000. Its semi-major axis, then, is around 36,500 astronomical units. By Kepler's third law, one orbit around the Sun takes it roughly 7 million years. Since it was thrown out, it has completed on the order of 600 such orbits. It had time, during those turns, to watch life form on the Earth, continents rise and fall, ice ages come and go, species appear and disappear. 40,000 years ago, when it was midway between perihelion and aphelion, on a planet it never came within a few thousand astronomical units of, cave lions were walking, and the last Neanderthal populations were still there. It does not know any of this. It has no way to know. It is only a cold lump of ice and dust, compressed over billions of years of cosmic silence. Its equilibrium temperature would be only a few Kelvin above absolute zero, a handful of degrees above the cosmic microwave background floor at 2.7 Kelvin. From its surface, the Sun is a point. More precisely, still the brightest point in its sky, brighter than any other star including Sirius, but a point. It does not shine enough to cast shadows. It gives no warmth. It dominates the eye visually, but physically gives nothing. Distance to that point is 70,000 astronomical units. Light from the Sun takes about 1/10 of a year to reach our chunk. Which means that if the Sun could somehow vanish entirely right now, mass and all, the chunk would find out about it more than a year later. Because information about mass, like information about light, travels at the speed of light, not faster. The constellations from this point are almost the same as we see from the Earth. Distance to the nearest stars, thousands and tens of thousands of astronomical units, is so large that a shift of 70,000 units to the side produces only a very small parallax. Proxima Centauri is still the same faint red point in the direction of Centaurus. Sirius is still the same blue beacon in the Great Dog. Polaris is still the same star in Ursa Minor. Otherwise, the sky is indistinguishable from the one you see over your roof. Individual planets do not appear from here. Even Jupiter, at this distance, is far too dim to notice against the Sun's glare. The Milky Way stretches across it in the same way. Night lasts forever, because there is no axis around which the chunk turns faster than the slow rotation on its own. Its rotation period, if it is even measurable, is on the order of tens of hours or days. Of those 7 million years per orbit, the chunk spends the overwhelming majority of its time near its aphelion. There, where we found it. Where it is cold, dark, nothing happens. Time flows slowly, because there is nothing to measure it by. Only once every 7 million years does it approach perihelion, but perihelion is at 3,000 astronomical units. Deep inside the Hills cloud, but still 75 times farther than Pluto. Even at its closest to the Sun, it does not come near enough to the planetary region for anything to happen. It will never become a comet. Its orbit does not cross the zone where the Sun could warm it enough. No heating, no tail, nothing ever visible from the Earth. In about 1 million years, its orbit will shift a little, because in about 1 million years, Gliese 710 will pass close to the Sun. The tidal force of the passing star acts on the entire inner Oort cloud at the same time. Some fraction of the bodies, perhaps including ours, will get a kick. Some will fly outward, some, on the contrary, will be pulled inward. For our chunk, the odds go both ways. Perhaps its perihelion drops to a few hundred astronomical units, and in 1 million years and change it becomes observable from the inner solar system. Perhaps its perihelion, on the contrary, grows and it moves even farther out. Perhaps almost nothing changes. We will not see any of it. But one thing will happen during its lifetime that is connected to us directly. In roughly 300 to 500 years, a silent aluminium cylinder will reach the inner edge of the region where our chunk lives, Voyager 1. It will enter the inner Oort cloud somewhere between the 24th and the 26th century. It will move through the sector of the cloud where our nameless chunk lives. Neither of them, neither the cylinder nor the chunk, will feel it. The cylinder went silent long ago. The chunk is blind and deaf. But the trajectories will pass closer than any human parcel to another solar system body has ever passed. And in 40,000 years, the cylinder will be 1 6/10 light-years from Gliese 445. By that time, our chunk will be already midway through its next orbit, somewhere off to the side of the Sun, still motionless in its endless cold. No exchange of messages will happen. No one will have read the golden record. No one will have met Voyager. It will have simply passed through that sector of the Oort and gone farther. And in the opposite direction, counting off its 2,500 years, comet Hale-Bopp is coming back. Right now, it is about 55 to 60 astronomical units from the Sun, still moving out, still slowing. Around the year 3260, halfway through its orbit, it will reach its new aphelion, somewhere around 370 astronomical units. Then, it will begin its fall inward again. By the year 4527 of the Earth's calendar, if that calendar still exists, it will again pass through perihelion, again develop its two tails, again be visible with the naked eye for months. The people of the year 4527, if there are people, will see it in their sky. It will be to them what it was to us in 1997, a comet that every newspaper will write about, a comet that every child will see, a comet that documentary films will be made about. Everything that we remember well from our own 97, they will live through again. And then Hale-Bopp will leave again for 2,500 years, and another one, and another. Until, in 1 million years, or 2, or 10, some new tidal wave of the galaxy, or some passing star, changes its orbit forever. Or until its nucleus finally crumbles from the accumulated heat and stress of close passes past the Sun. In its absence, the Oort cloud will keep hosting trillions of its neighbors. Most of them will never meet anyone. Not a single comet will they make. Not a single photon will they reflect back to us clearly enough to be noticed. They will turn slowly in their sphere, synchronizing by the Kozai leadoff mechanism into thin spirals we will never see, losing bodies to interstellar space and gaining new ones from other stars, from whose own clouds they came. What is left to say? All the questions we set up at the start now have their answers. Beyond Pluto lies not emptiness, but the dense Kuiper Belt, then the scattered disk, then the Hills Cloud, then the outer Oort Cloud, and then interstellar space. All of it inside our Sun's gravitational domain, which reaches almost halfway to Proxima. The bodies of that cloud are nudged into their long, slow falls toward the Sun by two continuous forces, the tidal gravity of the Milky Way and, on much longer intervals, the passages of nearby stars, with the tidal action of the galaxy also being the sculptor of the two-armed spiral hidden inside the inner cloud. The Sun itself does not end in one place. The heliopause sits at about 120 astronomical units, the orbit of the farthest known body around 1,000, the Hill sphere at 100 to 200,000. The real edge is a fuzzy gradient between the outer Oort and interstellar space, where the Sun gradually hands off to the galaxy. We have only just begun to see the cloud directly. The 21st of September, 2024, in the dome of the Hayden Planetarium, the two-armed spiral in the Ness-Vorny simulation. And from 2026, the Vera Rubin Observatory begins its 10-year survey, promising thousands of new inner Oort objects, the confirmation or refutation of Planet 9, and the first real map of a portion of the cloud. And whether we overlap with a cloud around Proxima Centauri, probably, in the most tenuous transition zone where neither cloud is dominant, but we will know for certain only when we can see bodies in those zones directly. The three interstellar visitors of the past 8 years do already tell us that an exchange of bodies between stellar systems is a real, ongoing process. Similar reservoirs are expected around many other planetary systems. Parcels travel between them, sometimes from one star to another, sometimes nowhere in particular, sometimes to us. Voyager 1 right now is about 25.5 billion kilometers away. It is 3 months away from becoming the first object separated from us by a full light day. In 10 years, it will fall silent. In 500 years and change, it will enter the inner edge of the Oort Cloud. In 30,000 years, it will come out the other side of the outer Oort. In 40,000 years, it will pass its first foreign star. Throughout all of it, it will be crossing space filled with 1 trillion icy chunks, meeting none of them. It will be passing them because they are far apart. It will be silent. And it will be carrying its golden record, with greetings in Sumerian and in Hindi, with the heartbeat of Andruyan, with images of human beings, with Bach's concerto, with the Navajo chant, with Chuck Berry's Johnny Be Good. That is what we sent. That is what will speak for us, if anything of ours ever reaches anyone. Comet Hale-Bopp is now at 56 astronomical units, moving slowly outward. In 2,500 years, it will return. Someone will see it. Two are drifting apart, in opposite directions. Voyager away from us forever, Hale-Bopp away from us, but with a promise to return around the year 4527. One cloud, one sphere in which they both travel at the same moment, each along their own orbit, each along their own thousands, tens of thousands, millions of years. 5th of September, 1977. 1st of April, 1997. 21st of September, 2024. 3 dates, 3 bridges across one cloud. We crossed it tonight in one journey. In reality, it takes much longer, and we will come back to this region many more times, with new images, new simulations, new discoveries, new probes. But one thing is now certain. The solar system is not a disk of 8 planets. It is a sphere of cold and silence 4 light-years across. It is older than any civilization, any memory, any language we speak in now. It contains 1 trillion bodies, each of them older than a human being, and it is our home, in its entirety, out to the very last icy chunk on its edge. Let me end with one short thought. The hypothesis of Oort, worked out by one man at a writing desk in Leiden in 1950, turned out to be one of the most durable theories of modern astronomy. It has survived 75 years. It survived the discovery of the Kuiper Belt, the discovery of the scattered disk, the discovery of dwarf planets, the discovery of the first inner Oort bodies. All of those discoveries have only refined the model, not overturned it. Oort today looks fundamentally the same as it did in 1950. Only now we know that it has an inner dense core, proposed by Hills in 1981, and that in the inner part there is a two-armed spiral, seen for the first time in 2024, and that the trillions of bodies inhabiting it may have very different origins, some local, some captured from other stars, some caught when the sun was still within its stellar birth cluster. All of that is annotations on the frame drawn by one man at a desk in the Netherlands. Such durability of a model is rare in science. Ordinarily, 50-year-old theories get half rewritten. Oort is the exception. Perhaps because Oort's hypothesis was built not on assumptions, but on direct observation of real orbits of real comets. It had an empirical foundation, not only a mathematical beauty, which meant that behind it stood real physics. One more thought. Of all the regions of the solar system, the Oort Cloud is the quietest. The inner planets are always doing something. Mars has dust storms. Jupiter has storms that come and go. Saturn spins its rings. Uranus and Neptune have winds exceeding 2,000 kilometers per hour. Even Pluto and the Kuiper region have moons moving, slow nitrogen ice sublimating and reforming, something happening. The Oort is almost motionless. The bodies out there move so slowly, and the distances between them are so large, that over the entire history of the solar system, almost nothing has happened. No collisions, statistically impossible at that density. No warming, the sun is too far. No geology, the bodies are too small to hold internal heat. Only very slow motion along elongated orbits under weak solar gravity, occasionally rearranged by the even weaker perturbations of the galaxy and passing stars. It is the quietest place in the known solar system. There is nothing quieter. Good night. Let the Oort keep turning in its perpetual dark, and let us not forget that we live inside it.